So today, yeah, we'll get into, welcome back, you guys, volumes by slicing. So we'll do what's called the slicing method first, and then we'll get into an alternate slicing method using solids of revolution. That's called the disc method. And the disc method with holes in it is called the washer method, and we'll actually break up this. It's a pretty long lesson, so we'll break it up into a couple different videos. So if you remember, before I start out, maybe I'll talk about volume of a cylinder for a minute. Do you remember how let's go ahead and draw a right cylinder here. Remember how with a cylinder, our volume was the area of the circle, which is the area of the base here, right? Area of the circle, in other words, one of the cross sections, if you will, times its height, right? Pi r squared times its height. That's kind of the idea behind finding these volumes by the slicing method, which is, so let's say we're trying to find the volume like this one pictured here in figure 6.1. What we'll do is, when we're taking that volume shown there, is we'll take a cross section. You see how we've got this plane that's like slicing through. If you can imagine like slicing a piece of bread, for example, and you have this base area, right? And so what we'll do is we're going to split this up into all these slices, if you can imagine slicing, 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 and then we'll sum up all these pieces of bread. Okay, and we'll do it with an iterative process. So if you can kind of imagine, it's like volume of the base times its height, right, for each of these cross sections. And then we're going to add them all up. So that's our slicing method in a nutshell. And so what's going on is we'll have this area. Here, let's give you a little notation with it. Here's the area. This is our area of the cross section. I want to write that in. And that's our width. In other words, our height that we showed you. It's kind of like the height of the cylinder, if you will. All right? And we're going to run an iterative process on this. Okay. In other words, a limiting process, right? Because if we add them up, if we just add them up having sliced the pieces of bread, we may have a little bit of error in there. And so we'll just run that limiting process just like we did when we're finding the area under a curve, right? We run that limiting process. So in other words, the limit as the number of those cross sections goes to infinity, which is the same thing as the width going to 0, right? We're using this limiting process of the area times its width, and that gives us this volume. Okay, so the volume of a solid with this slicing method is we're just going to go from A to B, area of the cross section. This is our area of the cross section. Again, this is just an iterative process, and that's our width, right? And the dx is representing our width, just like in 2 dimensions with the area under a curve, right? So that's what's going on. Technically, let's go ahead and practice some of these, and here's a few pictures as well. So you can see in this first one, if our cross sections were squares, right, and you were building, you're drawing all these, they kind of increase in height. I can't draw work beans so bad, but anyways, I'm going to try here. All right, it would go clear to the end. That would be our last one right here, and it kind of comes down. Anyways, that's kind of a very poor drawing on that, but anyways, we could find that volume, and we would use an area of a square as the cross section. That would be our A of x part right up here. Okay, and we go from A to B on that. Okay, here I've got half circles on it, right? We could draw our last one to be a little bit bigger. Oops, that's not very good. A bit bigger. I don't know if that's any better, but anyways, you kind of get the idea. And the volume there. Right? All right, let's practice. Let's practice a few here. The volumes by slicing. So our volume is, we're going to go from A to B, area of a cross section, dx. Okay. So here we've got a pyramid, 3 meters high, has a square base. So square base. Okay. So you want to think to yourself, see the little picture here, see how, bless you, we've got the square in here. So we know we've got this square, right, x times x, and we know the area length times width of a square is x times x, right? So we're going to have x squared in there. That's our a of x part, right? That's the area of the cross section. We're summing up all these cross sections, right? We're summing it up. And we're going from 0 up to our last value here on this plane on the very last. You see how it has a height of, it goes out to 3, an x value of 3 here. So we're going from an x value of 0 up to an x value of 3. We're summing all these cross sections up, dx. And this will give us the volume of this pyramid. Okay, again, imagine you're just slicing it up, right? You're slicing up this pyramid with all these squares. Okay, let's go ahead and run it. So we got x cubed over 3 from 0 to 3. We'll plug the 3 in. So it looks like we got 27 over 3, which is 9. And notice they did give us x's in meters, so this will be cubic meters, right? Volume is in units cubed. All right, let's take a look at this next one. Notice we've got this picture of this curved wedge. This is being, if you can imagine a cylinder for a minute, just to give you an idea of where this is coming from. And if you, like if we were to like slice this thing, you can imagine like I'm coming through with a plane here and like slicing that, if that makes sense. That's our picture that we have, is this wedge cut from a circular cylinder. Okay, and so it's got a radius here of 3. Again, this radius here, r equals 3. That's what it's showing. The picture, okay? Now, what may be harder to see is where's this stuff coming from. So let's talk about this for a minute. If I had the whole base, again, I know I only have this part, this wedge, right? But the whole thing's a circle, right? So x squared plus, centered at the origin, plus y squared equals the radius squared, right? So our radius here is 3. So we get x squared plus y squared equals 9. In other words, y squared equals 9 minus x squared. In other words, if I was solving for y, I got plus or minus the square root of 9 minus x squared. So on the top, like this part right here, that's the square root 9 minus x squared. And then you've got the bottom here, that's the negative. Right? So we've got this rectangular cross section. If you can see, let me kind of highlight. So here's our slice right there. So if I was blowing that up, let me just take that out. Okay. So notice here I have the area of this would be length times width, correct? And they're giving us this width. Can you see how this is x right there. I'm going out x amount and I'm matching it right there with this triangle, with a 45, 45, 90 triangle. So this is x height, if you will. The length from here to here, let me go over to the figure, that's from here to here. You see it? So it's from the top of that circle, if you will, to the bottom, from the blue to the red. So that length would be from the difference, right? Like if I'm up here, like let's say I'm up here at a y value of like 7, and down here at a y value of like -1. 7 minus -1, I'd have a distance of 8. I'd have a height of 8. Are you with me on that? So I just got to find the difference there. So square root of 9 minus x squared minus the red one, negative square root of 9 minus x squared. Well, what's that difference? Square root of 9 minus x squared plus the square root of 9 minus x squared is 2 square root of 9 minus x squared. That's this length, 2 square root of 9 minus x squared. And so that finally brings us to our volume. We're going from 0. Let me highlight this part. Let me do it in red here. From 0, x being 0, out to x being 3. Remember, this is that base was a circle. We had a radius of 3, right? So go 0 out to 3. We're summing up all these, from 0 to 3, we're summing up all these slices, all these rectangles are all being summed up, right? So the a of x part, this is our area of that rectangle. So that would be, the height of it was just x, right? That was that, and the length of it was 2, square root of 9 minus x squared. Okay, so that's where we come up with that formula. Let's clean that up. And then we just got to use some u substitution here. So we're going to go ahead and let u be that 9 minus x squared. So du would be a negative 2x dx. Notice I have 2x dx, but I don't have a negative. So I'm going to give it a negative, which means I got to offset it with a negative out front, right? So I give it a negative inside. There's my du right there. Offset it with the negative on the outside, so it's the same thing, right? So I can't just all of a sudden introduce the negative, right? And let's bring it up here. Let's go ahead and run it. So we got u to the 1/2. So u to the 3/2 all over 3/2. So 2/3. So we got negative 2/3 u, which was 9 minus x squared, from 0 to 3. Well, that's gone. And then I got a plus 2/3. 9 minus 0 is 9 to the 3/2. So we got 2/3, that's 9 to the 1/2 to the third, so square root of 9 is 3, and then I take the third, 27. 27 times 2/3, looks like I got 18. And these are whatever my units are cubed. All right, let's get into the disk method. The disk method is, we're going to be doing slicing with solids of revolution. So the simplest way to think about this, as I mentioned here, is to take a rectangle. We're going to rotate it around this horizontal axis. So if you spin this around, can you see how, I can't draw it at all, but you got the disk, right? Spin it around. And so that's what we're doing here. And then the volume of that would be the area of the base, all right, pi r squared, times the width of the disk, right? And r, capital R, this is our radius of the disk, okay? So your development from geometry, if you want to think about this, is we've got all these disks being summed up, and we're going to run this limiting process on that as well, where this is our width, the delta x is our width of that disk, right? So we're taking pi radius of the disk times the width of the disk. We're summing them all up with the limiting process right here, right? So the limit as n goes to infinity, or as the width of the disk goes to 0 again, right? And that'll give us the formula that we want. So this is for the disk method, okay? So here's a little picture of it down here. So again, here's our pre-calc formula that we represent with our technical notation so that we can do the summation of all those, right? The limiting process with the summation to get to our integral, right? So there's your connection there. And here's a picture of that. We're going to do it with a horizontal axis of revolution initially. Again, r of x here is the radius of the disk. D of x is the width of the disk. Okay, so that's kind of your baby. We'll do those. We'll do a bunch of those first. Then we'll get to when we spin it the other way eventually, and then we'll do it with respect to y. Okay. All right, let's do it with the square root of sine of x. All right, so you can see the square root of, here's our square root of sine of x. At least it's graphed from 0 to pi for us. And we're going to take that rectangle, right? There's our delta x. So that's our r of x on this thing. And we're spinning it. So if you can imagine, all those are being spun, right? All that's being spun. And we end up with that solid shown below. So our formula for the disk method, pi r squared times the width from A to B. And again, r of x, that's our r of x, right? Here's our square root of sine of x. So our r of x here, the radius of this, is the height. Right? Well, the height is the square root of sine of x. It's that y value of the function, right? And it's going to be squared. We're going to go from 0, x being 0, to x being pi on this thing. And so we have pi 0 to pi, square root of sine squared is just the sine. So we get the pi, take the integral of the sine, which is negative cosine going from 0 to pi. Let me clean that up a little bit. So I got negative pi cosine of x from 0 to pi. So negative pi cosine pi minus negative pi cosine 0. So our volume, we got cosine of pi is negative 1. That's a plus pi cosine 0 is 1. So it looks like I got pi plus a pi. This thing ends up being 2 pi as our volume of this figure. Alright, let's do a bunch of these. Find the volume of the solid. Let's go ahead and graph this thing. We got, usually our e to the x is like this, right? But we got y equals e to the negative x, so that'll reflect it about the y-axis. And it says find the volume of the solid generated by, here's this, e to the negative x. Y equals 0. Let me draw that. There's our x-axis. Y equals 0. X equals 1. Here's our vertical. X equals 1. I'm sorry, x equals 0, excuse me, to x equaling 1. There's x being 1, right? That vertical line. So it's the area bounded by those. Can you see it bounded in the blue, black, and red there? And we're going to revolve it, that region bounded, we're going to revolve that region about the x-axis. So I'm going to spin it. I have another horizontal axis of revolution. I'm going to spin it about that line y equals 0, right? So if you can imagine, I spin it. Right, here's my rectangle. This is going to be my r of x, but it's spun, right? So this is spun. This is spun. Anyways, it kind of looks like this. I didn't draw it too well, but you kind of get the idea, hopefully, from that. Does that make sense? You got all those little cylinders spun around. Here's our disk method. Pi, radius of the disk, squared dx from A to B. And so this would be pi, the radius here. All right, here's our radius. This is our rectangle, right? It's just that e to the negative x minus 0, right? It's the difference from here to here, right? So it's just that e to the negative x being squared. And then we're going from 0, x being 0, to x being 1, right? We're adding all these up, right? Of course, it's all those cylinders being added up. X being 0 to x being 1. So we got pi e to the negative 2x dx from 0 to 1. We're going to go ahead and let u be that negative 2x. So du is negative 2 dx. So I'm going to give it a negative 2, and I'm going to offset it with a negative 1/2 out front. So notice my negative 2 dx. There's my du. So I've got and now let's run the integration of e to the u. That's 1 over ln of e to the u. Well, our u here is negative 2x. ln of e is just 1. So this just ends up being negative pi halves e to the negative 2x from 0 to 1. We got e to the zeros, just a 1, so I got negative pi over 2e squared plus pi over 2, or if you want to take out, let's see, that would clean up, you could take a pi over 2 out if you wanted to. And you'd have 1 minus 1 over e squared. Be another way to write that. Or if you want to get a common denominator of e squared, there's another way to write that. This next problem is the u-triad problem. So a great time to pause this, go ahead and draw that and start working this problem, then you can check it. So here's our graph. We're spinning that thing around the x-axis. Let's go ahead and draw our radius of the disk. Here's our r of x, right? So this thing's being spun around. So if you can imagine the rest of this, right? This being, I can't draw what being, it's just so bad. Oh, the struggle is real. But anyways, right, that's your picture of that thing. So your volume setup would be pi radius of the disk squared dx. We're going from x being 0 to x being 8. We're adding all those up. A to b, so that'll be from 0 to 8. And that's y equals negative x plus 8 is that, this is y equals negative x plus 8 right here, right? That's that height. Of course, minus 0 down to the red. That's that radius squared. We got negative x plus 8 times the negative x plus 8, so we got x squared. All these are zeros, right? So it's all gone. So it looks like we got there it is, 512 pi over 3 units cubed. All right, let's keep going here. This is a good u-triad problem. I did give you the picture. Maybe I shouldn't have given you the picture, but go ahead, pause it, and try that one. So if you want to go ahead and check yourself on this one, you've got your radius here, r of x. That's our function, e to the x plus 1 minus 0, right? It goes down to that x-axis. That's that height or radius of the disk that we're spinning, so it'll be squared. And then we're going from 0, x being 0, to x being 1 over here. And then it's just a matter of cleaning that up, right? You can pause it here if you need to pause it before we move on. All right, let's move on. This is another u-triad problem. Let me give myself a little bit of room here. So go ahead, pause it at this point. Go ahead and graph it and spin this thing about the x-axis again. And on this one, we'll walk through a little bit of the graph here. I'm thinking to myself, maybe the easiest way to think about this graph is to think about it's part of a circle. X squared plus y squared equals 9, right? Which is, so here's my r squared. So it's a radius of 3. 1, 2, 3, 1, 2, 3. Like there's our circle, but you know, if I was going back and solving for y, I would have plus or minus. But we were only given the plus one, the top half of this circle, right? The square root of 9 minus x squared. We were only given the top part. Let me do it in red here. we're only given that part of the circle, right? Square root of 9 minus x squared. All right, so there's our graph. And then let's look at the rest of this graph here. We got y equals 0. Let me do that in green. Here's our y equals 0. And we're revolving it about this x-axis, spinning it around. So here's our r of x that we got to spin around, right? So it's just gonna end up being sphere, right? And so we've got this volume is pi r of x squared dx a to b. So we're going from -3 to +3. Square root of 9 minus x squared is being squared. That'll undo the radical. Now we can go ahead and integrate that. So we got 9x minus x cubed over 3 from -3 to 3. Yeah, let's see, 27 minus 9. Looks like we got 18 pi plus 18 pi here, 36 pi units cubed on that. I think it's worth noting we'd mentioned this is a sphere, right? This in this scenario, this ends up being a perfect sphere. If you remember from geometry, so sure we used calculus to do this, but from geometry, the volume of a sphere was this, 4/3 pi r cubed. Well, what's the radius here of this sphere? This radius is 3, so this is actually in geometry, right? Oh my gosh, same thing. Look at that, right? All right, let's get a little picture of this, and let's revolve this about a different coordinate axis, but it'll still be around a horizontal axis. So we'll still do this with respect to x. But let's think about y equals 2 minus x squared, or maybe you want to think about negative x squared. So I flip over a parabola, I bump it up to right, and so I've got, here's my parabola, not drawn very good, but whatever. Anyways, we got that one, and then y equals 1. Let's draw that. Here's y equals 1. And we're going to do it about that same y equals 1. We're going to go about this line. I'm going to revolve it right around that. So let me kind of erase some of this and draw this a little better. Let me cut this off right there. All right. First of all, where do they intersect? Where's the intersection of y being negative x squared plus 2 and y being 1? Where do they hit? You probably see it right there, but if you don't, x squared equals 1 square root. You get plus or minus 1. So this is 1 and negative 1, right? That's where those two intersect. We're going to go ahead and take this. Here's our radius of the disk that we're going to spin. So if you can imagine, this is kind of like a football here, right? I'm spinning all those, right? And that's my radius right there. There's my r of x right there. So let's go ahead and give myself a little bit of room here. So our volume here is pi r of x squared dx a to b. So our r of x, so that'll be 2 minus x squared is this top part right here, the top of the football, right? 2 minus x squared minus, because it only goes down to the red, right? I don't want this, I don't want it clear down to the x-axis. I don't want that. I only want this in green right here. So I got to subtract the height of this, subtract y equals 1 to the 1. Let me do it in red here. To the 1. And this is all squared, right? So this is, again, this is the radius of the disk. Guys, the difference between those heights there, right? Top minus bottom. So we got 2 minus x squared minus 1. So I got 1 minus x squared is being squared. So we got 1 minus x squared times 1 minus x squared is 1 minus 2x squared plus x to the 4th. And we're going from negative 1 to 1, right? Negative 1 to 1 is my lower and upper bounds here. And so let's go ahead and integrate that. Oops, don't forget your pi out front. Almost forgot that. So we got pi, and then we got integration of 1 and 1x minus 2x to the 3rd over 3 plus x to the 5th over 5. Negative 1 to 1. Let's see, I have the so we got pi 8 pi 15ths plus 8 pi 15ths. So our volume is 16 pi 15ths on this. All right, let's go ahead and rotate now about a vertical axis. So same concept. This time we'll have it like x. It's like x of y, right? The function is defined in terms of y now. So x equals 2 over y. Instead of like y equals 2 over x equals 2 over y is this, right? Right there. And we're going to spin that. So we'll take the radius of the disk and we'll spin it, in this case, around that y-axis, right? We're spinning it around the y-axis. And you can see with the picture on the right is a much better picture of that, right? And so it'll be r of y as the radius of the disk. And then we'll go from C to D, right? So from C to D, whatever the y value is, to whatever the y value is up top. Low to high there. Okay? All right, so let me erase this. We'll go ahead and do this problem. See what we get here. And, you know, some of these problems, it'll give it to you like this, so you'll have to solve for x. So multiply both sides by x, divide by y there. Right, so we've got x in terms of y. X equals 2 over y. Again, this is that curve, or at least part of that curve, 2 over y. We're going from a y value of 1 to a y value of 4, and we're spinning it around the y-axis. So from y being 1 up to y being 4. That's from y being 1 up to y being 4, right? So we got 4 over y squared. Let me write it this way, 4y to the negative 2. And let's go ahead and integrate it. So we got, oops, I almost forgot my dang pi again. My goodness. So we got pi. Now let's integrate it. I got 4y to the negative 2 plus 1, negative 1 over negative 1. From 1 to 4. Clean that up. So I've got negative 4 pi all over y from 1 to 4. Right, if I write that cleanly. Put the 4 in. Put the 1 in. It looks like we got negative pi plus 4 pi. So our volume here is 3 pi cubic units. Alright, find the volume of the solid generated by revolving the region between the parabola x equals y squared plus 1. You know, maybe I'm thinking this. At least this is how I picture it. So I got square root of x minus 1, the top and bottom half of that. Right, if I'm graphing this, let me erase that. Square root of x minus 1. So it looks like the square root function, but it's to the right one. There's the top, square root of x minus 1. There's the bottom of that. Square root of x minus 1, right? So this is x equaling y squared plus 1. Now let's do the line x equals 3. There's x equaling 3. And we're going to go about that line, x equaling 3. So let's spin it about that. Again, a vertical axis of revolution. So we've got to do this all with respect to y. Right? Where do these things intersect? I'm trying to figure out where does this x equaling y squared plus 1 intersect with the line x equaling 3. In other words, where does y squared plus 1 equal 3? Looks like a plus or minus root 2. Of course, you could plug in 3 as well. So comma root 2 is that one, and this one's comma negative root 2. Of course, the x value there is 3. Right? I want to emphasize the y there. And our cross section, let's go ahead and draw our r of y. So here's our rectangle that we're spinning. So if you can imagine, that's spun. All these are spun, right? Spinning that. That's what we're doing right there. Right? Give myself a little room. Got the volume is pi from C to D, representing, C to D, representing y equaling C, y equaling D. Okay. And when you're doing these, you want to go the right hand minus the left hand. So the right hand is x being 3 minus the left hand is that y squared plus 1. That gives you the length of that, or radius of that disk, right? The length of that rectangle is the right hand minus the left hand. So that's 3 minus that y squared plus 1. That is our r of y. And we're going from a negative root 2 up to a positive root 2 on this. So we got 3 minus y squared minus 1, so 2 minus y squared is squared. Don't forget the dang pi that I always forget. 2 minus y squared, 2 minus y squared. We got 4 minus 4y squared plus y to the 4th dy, negative root 2, positive root 2. And then we'll keep going with that. So we got 4y minus 4y, 5, negative root 2, positive root 2. Let me do change that to a plus, so that'll change all these signs in here. So I'm combining. See how they both got a pi in front there. There's your 8 root 2 and so on. All right, there's those like terms. And so anyways, and then 8 root 2 over 5. Okay. So get a common denominator of 15, looks like. So I'm gonna, this is over 1, so 15, 15, let me multiply 5 and 5, this and 3, and 3. And that'll end up being 20 root 2 over 15 minus 80 root 2 over 15. 4 root 2 over 15. Over 15. I gotta give myself more room. And there we are. Cut it off. We'll do the washer method next time. Thanks so much for watching. See you next time.